Okay, so let's start with the second installment of this Corona series. And today I want to explain how a completely different model, that is the model from the point of view of the susceptible, who gets infected at some time, how that looks like and how it couples to the SIR model or something like the SIR model that I introduced last time. So I start with an example which will be also of some interest later because I want to compare later on the probability to die from corona to the probability to die at all in the next year for someone who gets infected. So let's start with the simplest process that I can think about in continuous time. So time is just our ordinary time. But the process, of course, is process of death. So it is, for each individual, it is a tau one time, when he is dead. Now, how does this couple at all to something like an ordinary differential equation? So something which has a rate of change per time. So what has a rate of change per time is the probability that you yourself die later than t. So here we have again the rate of change is again, it's of course negative because the probability will always be smaller with growing time. So it will be proportional here to the probability that you are still alive at the time t. Now, sometimes you see that also written in a different way, but this is basically exactly the same formula that I have there, except that I took here a small finite h, and here I went to what we call an infinitesimal description. So the probability that tau will occur between t plus h and t, if you know already that tau is larger than t, will be proportional to this alpha times h. That's what it means. And this is the basic type of formula or model that we use to describe a process which is basically, we would call it mathematically a 0-1 process in continuous time. So remember that the quantities for which you can give a formula for the rate of change, these are just probabilities. Now, what does that mean at all? After all, for the individual, it's something which is completely unpredictable. So you don't know when this tau is occurring. The only thing that we can try to predict is the frequency of this event if you have many individuals. And that's actually what is the point of view that you are taking when you look at stochastic processes at all. Now, I prepared, as before, one blackboard behind, and now instead of the death process, we are looking here at a process which is modeling what is happening in an infectious disease, let's say, like corona. So I have a very simple model. I will say that an individual gets infected at a time t. After a certain incubation time a, it starts producing a virus load, which here will be just constant up to the time t plus d, tau plus d, when the infection will stop. So d is the duration of the infection here. On top of this, you have a random time, again, so a time which you do not predict, when you are discovered to be an infectious individual, and then you are removed. So you are put under quarantine. So this rate at which you are, or the probability at which you are going to be discovered after this time A, because before there is little hope to discover you, this probability, I just put it here for the sake of simplicity with a constant rate. But it's the same kind of a process that we discussed below there. Now, we still have to say, what is the rate of the infection itself? And the rate at which the infection occurs, that should depend on something which we call the contact rate alpha, and it should also depend on a quantity which is the relative frequency of the not yet removed individuals who are infectious. So that means that you are infectious if, for you as an individual, that's what I call tau ij, if your tau, the time of infection is actually smaller than t, but not only smaller than t, so it is tau plus a has to be smaller than t. And on the other hand, you are not yet removed, that's this bij that I write down there, then you contribute in this simple model with a constant virus load to the kind of infectious environment for the average individual that we have there. That is what we call somehow, because we are not, in this particular case, we are not interested in different contact rates between different individuals. We just put in here 1 alpha at this moment. Then we call that the same as you do in theoretical physics. We call that a mean field model. So the mean is here, what we are writing is this sum, it's the average sum. It's the frequency at which you observe infectious among your population. So this is the first part of it. Again, I will have to do a little cleaning of the blackboard, and then I will be back to you. So just a moment, please. Okay, so I wrote down in the meantime the kind of formula that you get in what we call the large n limit, the limit of large numbers of this kind of frequency, which is predicted by the stochastic process which I described before. And it is slightly more complicated. Well, actually, it is quite a bit more complicated than what this simple SIR model that I wrote down before, because now what does not disappear from the equation is the time since infection, tau, that an infectious individual is running. Because, I mean, after all, the individual will be infectious from this, time after infection, time A, up to time D, and then it will cease to be infectious. Or it will also cease to be infectious if it is actually removed. And that is the meaning of this first equation. It's an equation in the variable, what I would call t plus tau. Sometimes we call that is the characteristic of a partial differential equation. Partial differential equation means that I have here two different variables, the time t and the time tau since infection, that plays a role for the infectious individual. But it plays a role only for the infectious individual. For the susceptibles, of course, they don't have an additional parameter t. So S, the relative frequency of the susceptibles, that still depends only on t, on one variable. The point that I will make in the more mathematically oriented episodes is that actually if you are just interested in where the epidemic starts and where it ends, so you know that you are starting with, let's say, 0 infections and a certain frequency of susceptibles, and you want to know where the epidemic will go. It goes to a lower rate of susceptibles, of course, in the end, and again, no infection at the end of the epidemic. If you are only interested in that, then you can reduce this much more complicated system to an ordinary SIR system. And this ordinary SIR system will be just of the form, and let me write this down. It will be of the form dt of S is actually something which I now call capital A. It's again just a quantity, A times S with a minus sign. And, sorry. And dt of I will be the same thing. So it will be just this A times S. Now, usually you would see here this beta. You remember that? A times S times I, of course. And usually it would be ASI minus beta. In this case, it is just minus I. So beta is, for this reduced system, beta is just set to be equal to 1. You could say by rescaling of time, or taking the time, which is actually the time for the duration of the epidemic. And now the A, I can also give a formula for this. So the A is just the same thing as what we had. It's the alpha. And then you have here this integral which is sitting there, A to D. And here you have E to the minus delta tau d tau. And I'll explain this. So there is a formula just in this particular case which couples the new variable which replaces the old SIR variable to the old variable alpha, and this kind of rate of removal by quarantining, which is in this slightly more complicated system. What we don't have is we don't have the equivalence of the evolution in time of the epidemic with this kind of very much reduced system. But what we have is the final outcome of the epidemic will be, how shall I say, monitored by the evolution of this much simpler equation rather than this partial differential equation, or sometimes we call it also a delay differential equation that we have up there. So that is to tell you that somehow you can reduce to SIR model because certain, how shall I say, certain predictions about the outcome of an epidemic for the much more complicated model that I'm writing down here will be equivalently modeled by a reduced SIR model. Thank you.